keyboard on this computer. Thank you. So I'm going to start off with the y. 3t squared minus 2t. And then after that, I'll take care of the x's. So x is equal to 2t to the 1/2 power. I'm doing it that way because eventually we're going to have to divide the two. And the most common error that I've seen with this concept is that just people divide them in the wrong order because they're so used to doing the x stuff first and the y stuff. So just something to keep in mind. So I'm going to say dy dt is equal to 6t minus 2. All right, so this is ordinary differentiation, not implicit. Don't overthink it. It's just power rule, both cases. All right, so the next one would be dx dt would be just t to the negative 1/2. All right. So then if I want dy dx, I'm going to find the quotient of those two. So 6t minus 2 divided by t to the negative 1/2. All right. Now, if this were the only question, I'd say, all right, we'll just leave it at that. Didn't say to simplify, but we got a little problem here, Houston, and that is we got to find the second derivative. And if we find the second derivative, it probably would make our lives a little bit easier if we had a cleaner first derivative to work with. All right. So that's how we're going to handle it. So I'm going to rewrite this as t to the 1/2 times 6t minus 2. Oop, that ran on me. And then I'm going to distribute the t squared, t to the 1/2. No matter how much I want that to be t squared, it's not. 6t to the 3/2 minus 2t to the 1/2. All right. A little bit nicer. I mean, it's by no means a work of art, but it's still something. All right. So now I want to find my second derivative, which is, you refer to the formula, it's just a matter of taking the first derivative that we just came up with and dividing it by dx dt. All right. So, and you know, I'll just kind of run through that again, just the theory of it, because it's d of a second derivative of the y function. All right. So compare that to what we have. That's the derivative with respect to x, where that y is now becoming dy dx by the model. Right? We're following the model. It's like, normally I would say, well, I want to find the derivative of y with respect to x, but if I want to find the second derivative, I'm finding the derivative of the derivative. And so what does that look like? We would say, with respect to t, just by following this rule, d of this dy dx divided by dx dt. All right. It's just.
I have a question.
Sure.
How come we're following this formula instead of doing like the power rule like we did for the first derivative all over again?
Because, and that's a good question. If you look at our first derivative, we have dy dx, but it's in terms of t. All right, so the question would become, well, how do I take the derivative with respect to x if the variable itself is not x? Would the whole thing go to 0, or is there some other way? Right? So,
okay.
yeah, so the other technique comes into play. Now, if the whole function was if it somehow magically worked out that it was all in terms of x, then you could go the process of just take the derivative again, you know, using power rule, but you got to do it this way, right? So what that's telling me is that I need two ingredients. I need a derivative with respect to t of dy dx. So that's part of it. So that's my 6t to the 3/2 minus 2t to the 1/2. So, sorry, notation. The derivative with respect to t of that. Which will then end up being 9t to the 1/2 minus t to the negative 1/2. All right, so that's the top part. All right, so that's this part right here. The dx dt, there's no no mystery there. We already have that. So we could actually jump now to dy, d2y dx squared. The top we know is going to be 9t to the 1/2 minus t to the negative 1/2. The bottom, I'm going to change the red for those keeping score at home. dx dt, we noted over here, is t to the negative 1/2. All right, we already figured that out. So that's this guy. So the bottom of my fraction is going to be t to the negative 1/2. Now the directions, and you know, like for the sake of learning math and you know just trying problems and practicing and developing proficiency, you want to simplify. But on a test, if a question doesn't tell you to simplify, you don't have to simplify. And in fact, I would even go the other way and say, if the directions do not tell you to simplify, if they do not tell you to simplify, do not simplify. It's not a question of you don't have to. I'm telling you don't. Because if you make a mistake, then you're losing credit for something that you never had to do to begin with. All right. So that's my word to the wise for today. All right? There are plenty of other teachers that are going to make you simplify just for the hell of it. I'm not one of them. I'm just going to split it up. All right, dividing each part of the numerator by the denominator. The second part goes to 1. The first part, keep the base, subtract the exponents, and we're just going to get a clean t. So 9t minus 1. And so that's my second derivative. Kind of crazy to see how out of all of this mess that you get such a clean answer, but it's also kind of crazy to see that something that looked like it would probably be pretty easy had a lot of moving parts to it. And really, if you think about it, this is all power rule. So it's like, whoa, what are we going to be on the hook for when we start talking about trig and exponentials and logs and stuff like that? Same. It'll never be any more difficult than this. You know, like you kind of think like, oh, it's going to be much worse with those crazier functions. Well, those are rules based. If you know that the sine has a derivative that's cosine, and the natural log of x, for example, has a derivative that's 1 over x, then that gets you a lot of the way. All right. So let's look at number 2.
Excuse me.
Sorry, let me pause. All right, so number 2, given the parametric, so far the same, write an equation of the tangent line to the curve at the point where t is equal to 3 pi over 4. Right? So a couple of different moving parts here, and they're both pretty important. One, you see tangent line. Right? Now, I don't want to toot my own horn or take too much credit for things, but I think that I came up with a way involving tangent line that just makes all the sense in the world. Now, you may know the tangent line equation as y equals mx plus b. You might know it as the point slope form of a linear function, which is y minus y1 equals m times the quantity x minus x sub 1. So all algebra 1 stuff. I go with this method. Y equals m times x minus x sub 1 plus y sub 1. Right? Now this is not like black magic. It's not anything earth-shattering. You know, and if you really think about it, you're like, wow, this guy's taking credit for really something very minor. And I'm looking at it more like, why doesn't everybody teach it this way? Because like I said, most people know it as same as y minus y1 equals m times x minus x sub 1. Like that's the one most people are familiar with. But aside from this being solved for y in terms of x, which makes it graphing calculator, graphing by hand if you want, very friendly for those sorts of types of problems, it's also in a standard form. You know, if you think about every other type of standard form, whether it's for a quadratic, a cubic, a trig function, an exponential function, a log function, they all take on this form of something as a coefficient, x minus something, then some other business going on, plus something else, all right? So really, this is following that same model, and whenever you think of a line equation, this is really what you should be thinking of, all right? An alternate form of it, if you want it to be really consistent with all those other types of functions out there, we could even say y equals a times x minus h plus k. No, I don't need a close paren on that one. All right, because the only difference between this and a quadratic function would be a power of 2, cubic a power of 3. The only difference between this and a natural log function would be if I snuck an ln in between the a and the first open paren. All right, so this is the way. So I would go with this approach. If your teacher showed you this way, then maybe I'm not as impressive as I think I am, but I'm willing to bet that the far majority of you learned it as some other way. And I've even heard people say that they've and I'm just gonna put a whoosh right through that one, that they've had teachers that said, forget this y minus y1 equation. They wouldn't even teach that. You'll never need that. Just use y equals mx plus b. It's so much easier. Like that, it's not a question of what's easier. It's what's going to work all the time. You know, sometimes the thing that's going to work is a little bit more difficult, but it's going to work. All right. So off my soapbox, down to business here. So dy d. You know, I'll just rewrite the y. Y equals 3 sine t. And then I'll just jump right into it. Dy dt. Derivative of sine is cosine, so 3 cosine t. Then we have x equals 4 cosine t. Derivative of cosine is negative sine. So 4 times negative sine of t, negative 4 sine t. All right. So I need dy dx which is the ratio of these two. So we got this guy here. I'm going to color code a little bit. So 3 cosine t. Poor quality straight line, so I'm going to use my straight line tool. And then on the bottom, I have -4 sine t. Now, we should know, hopefully, that this is the same as a -3/4 cotangent of t. In my experience, people are very familiar with their sines and cosines and not so much with their other stuff, in terms of trig ratios. So what I'm going to do is I'll make a note that this is the same as -3/4 cotangent of t. I'll put parentheses on it so it doesn't look too weird. But we're going to work with the cosines and sines. All right. So now we want to write the equation of a tangent line. Right. You got to be careful. It's very commonly mistaken that the equation of the tangent line is just the derivative with substituting values, and so people will just plug in the 3π/4 and call it a day. We need the equation of the tangent line. So we need the slope and we need a coordinate, right? So I need 3 pieces of information. I need an x value, which is based off of our knowledge of 4 cosine of t. I need a y value. I'm getting my color schemes messed up here, so let me change this over to blue. Sorry, I think that was incomplete. So
also, isn't it supposed to be -4 cosine t?
-4 for the x value.
Wait, never mind. I think I'm mixing myself up between the two.
Yeah, I think I was worried I was doing the same thing. Okay, so the y, I was more concerned with getting my color scheme right that I started losing track of what I was writing down. Let me move this back up. And then I need my dy dx. And here I'm going to leave it as 3 cosine t over -4 sine t. All right. So these are the 3 pieces of information I need, because here we're going to get the h and k values if we're using this model. And here we're going to get the slope m, or for using this model, a. It depends on how you want to look at it, but basically you're going to get the 3 important values that go into the equation. All right. So I need x at t equals 3π/4. Notation becomes pretty important in this course because it is very easy to lose track of what you're doing. In math, I guess it's very easy under the best of circumstances, but in this course, we're going to do a fair amount of computation and writing that it really does become kind of all over the place. So the notation helps keep it organized. All right, so 4 cosine of 3π/4. And then I'll need 3 sine of 3π/4. All right, cosine of 3π/4, so the unit circle, that's radical 2 over 2, negative radical 2 over 2. And sine of 3π/4 is positive radical 2 over 2. So we have our x and y values. Of negative 2 radical 2 and 3 halves radical 2, or 3 radical 2 over 2. I kind of like it coefficient first, then radical, but there's different schools of thought on that. So we got that part. So we have the x1, the y1, or the h and k, depending on, you know, which one you subscribe to. And then now we just need the slope. All right, so benefits of digital ink. So now I just have to pop in a 3 pi over 4 for t in my derivative function. So dy dx when t, or given that, such that t is equal to 3 pi over 4 is going to be 3 cosine 3 pi over 4 over negative 4 sine of 3 pi over 4. All right, so we've already run some of these computations. We know that cosine of 3 pi over 4 is negative rad 2 over 2. So 3 times negative rad 2 over 2. Now, if you happen to know your cotangent rules, then you can save yourself a little bit of time, but I'm kind of assuming that that's not necessarily the case. Or at least it's something that we can take some time and review one of these days. Sine of 3 pi over 4, we've established that that's radical 2 over 2. Opposites divide to equal negative 1. So we're talking about negative 3/4 times negative 1, which is going to be positive 3/4. Right? So then we have all of our ingredients. Now it's just a matter of putting it together, mixing it up, and making some delicious pie or a nice salad or something. I don't know, something good. So this is trying to keep the color scheme. This will be my H, my K, and this is the A. So my final answer is going to be y equals 3/4 x minus 2 rad 2, so x plus 2 rad 2, plus the k value of 3 halves rad 2, so plus 3 halves radical 2. I mean, that takes a little extra doing, but really, if you think about it, I mean, you know, calculus, really, if you think about calculus, any level of it, the hardest part is never the actual calculus. The part where you're finding a derivative or an antiderivative, it's all the pre-calc stuff. You know, even in this class, you'll find that anything that becomes even remotely challenging has nothing to do with the calculus components. It's all the pre-calc stuff. So knowledge of the unit circle, you know, derivative rules. Those, I mean, you can research that. You know, like, okay, you forgot that the natural log of x has a derivative of 1 over x. Okay, well, Google it. You know, that's fine. It's knowing these kind of relationships and actually carrying out the work. That's where things start getting a little dicey, right? And also, you know, step one. What is step one? You know, people have trouble with that all the time, where it's like, if I don't know what to do first, then I'm all out of luck. Write the equation of a tangent line to the given, to the curve. It didn't say find the derivative. It didn't say find dy dx. If you don't know that writing the equation of a tangent line it implies finding a derivative, then you're going to be jammed up on that also. Right? So the one good thing is if you're strong in your notation and vocabulary from Calc 1 and Calc 2, then that's going to serve you well here. All right. And so, that's not to say that everybody who's, a little weak in those areas should have an oh crap moment right now, but there is a reward. There is a reward for having listened and done your part when the teacher said, you got to go home and you really got to get to know that unit circle. It's gonna make such a huge difference down the line. Some of you are like, yeah. And some of you are like, all right, better get to it. It's going to matter at some point. The ones that said, I better get to it and it's going to matter at some point, you're now going to start reaping the rewards big time, right? Because a whole lot of this course is unit circle. So it's never too late, but that unit circle should, like the back of your hand. Right? Next class, we'll talk more about the unit circle, how to create it, and some games and things like that to help you memorize it if you haven't already done so. And if you have memorized it, then those games are going to be pretty easy. Number 3, find all horizontal and vertical points of horizontal and vertical tangency given the parametrics. All right, so vertical tangents, horizontal tangents. It's all about where the slope is equal to either 0 or where the slope is equal to 0 or where the slope is undefined. All right, so let's get into the act of finding the derivative. So I'll rewrite my y. I didn't turn off my line draw tool or my geometry tool. So y is equal to t squared minus 3t plus 5 dy dt is equal to 2t minus 3. Different color. X is equal to t squared. Oh, poor quality equal sign. Let me fix that.
Professor?
Yo.
Can you just go back to the equation of the line? Let me just, because I can see it.
Yeah, you got it. One sec.
Please.
Zoom out.
Is x equal to t squared plus t or t squared plus 2?
Thank you. Thank you. T squared plus t, which gives us 2t plus 1. All right.
Thank you. I got it.
No problem. No problem. So, derivative dy dx. Two t minus 3 over 2t plus 1. All well and good. Oh, a little off my screen here. So all well and good. We have a derivative. That's wonderful. We got to think about, way back to Calc 1, what it means to be a horizontal tangent. Right? So you want a continuous differentiable function on the interval, assuming that it is a function. So I'm speaking Calc 1 language right now. Parametrics, we know they can go every which way. So continuous function, in this case, we say a smooth curve for all points. But we want the slope to be equal to 0. dy dx, again, is the instantaneous rate of change, also known as the slope of the tangent line. Right? So if I want the horizontal tangent, I want to take my derivative, dy dx, and set it equal to 0. All right, so 2t minus 3 over 2t plus 1. As it turns out, the 2t plus 1 is going to be irrelevant. But the issue that we're going to run into is that it won't always be irrelevant. So we got to be careful about that. So what a lot of people want to do is they just want to say, okay, well, it's really just the dy dt, set it equal to 0. Let's make that the rule. Sometimes there's a common factor between dy dt and dx dt that cancels out. That common factor could be it's weird, but it could be a horizontal tangent. It could be a vertical tangent. It could be a corner. It could be a cusp. It would take a lot for it to be a corner, but it could be a cusp. There's a lot of things that could be going on there. It could simply just be where the function or the equation is undefined, right? So we don't want to immediately dismiss it out of hand. We need to investigate, right? So we're going to cross multiply, right? Because it's a proportional relationship, and we get 2t minus 3 is equal to 0. Solve for t, you get t equals 3/2. All right. Now you got to think about what a point is. A point's a location. Point, also known as a coordinate, right? So if first off, I haven't verified that this is actually a point where there would be a horizontal tangent, so I got to get into that. But it's also something where I haven't given a point anyway. I've given a t value, a moment in time where I can expect there to be a point of horizontal tangency, right? So one thing I could do now is pop this into x and y and see what coordinates, the coordinate this gives me. So in the x function, t squared plus t, that's going to be 3/2 squared plus 3/2. And for the y, a little messier, it's going to be 3/2 squared minus 3 times 3/2 plus 5. So we're looking at 9/4 plus 3/2, which is the same as 6/4, so 15/4. And then for the other piece, it's going to be 9/4 minus 9/2 plus 5. So 9/4 minus 9/2 is negative 9/4. Right, common denominator, you have 18/4 plus 5. Now 5 is the same as 20/4, so 20 minus 9 is 11. 11/4. Just for the record, sometimes I get lazy and I do math by hand. If that sounds weird, it's because I'm just a weird guy. I just didn't feel like taking out a calculator. You can, by all means, use a calculator for this. And certainly check my math, because when I start getting lazy and sloppy like this, sometimes I run into trouble like that. So the point would be 15/4, 9/4. Now we'll cross the bridge in a second of whether or not that is actually a horizontal tangent, but let's go through the process of vertical tangent first. All right, for vertical tangent, we want dy dx to be undefined. You could write undefined in a variety of different ways. The way that most people choose to do it is some constant over 0. Right? You could even make it just 1/0. Right? So 2t minus 3 over 2t plus 1 would be equal to some constant c over 0. Cross multiply, you get c times 2t plus 1 equals 0, but then the c goes away anyway. So 2t plus 1. That's why I was saying you could just write it as 1/0, because it's just going to go away anyhow. So t would be equal to negative 1/2. All right. So that's a possible point of vertical tangency. We'll have to investigate in a minute whether or not that's actually the case. All right. So pop this in for x and y. It's t squared plus t, so plus negative 1/2, or really just minus 1/2. So a quarter minus a half, negative 1/4. And then the other piece,
So on that part, you just divided the c by to 0, right?
correct, exactamundo. All right, so for the other piece, it's negative 1/2 squared minus 3 times negative 1/2. Poor quality, negative 1/2, so let me just clean that up, plus 5. So a quarter plus 3/2 plus 5. So that's really 6/4 plus 1/4, 7/4, so 27/4. Maybe. Let's see. I think so. So the point here would be negative 1/4, 27/4. All right. So then the big question would be, all right, well, is it or isn't it? Or are they not? All right. So for that, we're going to kick over to Geogebra. All right. And so that's the, I don't want to say it's the moral of the story, but it's a very important component of the course is that you develop some kind of proficiency with the technology, Geogebra or Desmos, either way. But, and if you have a graphing calculator, you can use a graphing calculator, but this remote environment, it's too much to go that route, I think. All right, so I'm going to pull up Geogebra on a browser. I'm going to leave this up for a second for those of you who are still writing, because I don't want to jump the gun there, because that's like the #1 thing I'm ever guilty of. But I'm going to open up Geogebra again. And then I'll walk you through how you can graph the parametrics on Geogebra, because I would do Desmos, and we've looked at that before, but since you're working on a tech assignment directly related to Geogebra, it's like, why not, right? So I can go one way or the other. This is the way I choose to go.
Quick question. So the first point has a horizontal tangent line, and the second point that we calculated has a vertical tangent line, or should have?
Should have, and we're going to verify that now graphically. That's the plan anyway. All right, so I'm going to stop the share on the iPad, and I'm going to start the share on the desktop, because that's just the way life is now. So in the waffle, you can go into just a regular graphing calculator because this is a 2-dimensional graph. You don't need 3D. You could also use the classic function, either way. But what you want is the curve function. So if you type in curve and open parentheses, it asks you for 2 expressions, a parameter, a start value, and an end value. All right. So then that's really all we need, because the two expressions are the x values and y values. All right. So whenever you plot a curve, you need to tell it what expressions you're using to plot x, the x component, what expression you're using to plot the y component, what the variable is, and what the domain is, right? So open paren, my x equation is t squared. So the caret symbol as a shortcut, if you're using a keyboard, gets you a power, but you could also use the, you see the display here, you can just use this. It's up to you. If you're on a phone, then you're using this keypad, but if you have a keyboard available, a lot of the keyboard shortcuts are exactly what you think they would be, all right? The right arrow to get out of that, so whether it's the right arrow on the keyboard or the right arrow on the virtual keyboard, plus T. So that's the x component. So you're not putting x equals, you're just putting the body of the function, all right? T squared minus 3t plus 5, oh, right arrow, minus 3t plus 5, comma, so you have your x component, your y component. If you had a parametric equation in 3 dimensions, you'd have a z component. In 4 dimensions, you'd have an additional component. Tell it what the variable is. My variable is t. And I wanted, well, this is, well, I was going to say it's a trig problem. The last one was a trig problem. These numbers that we're interested in are kind of small. 15 quarters, that's around 4. 11 quarters, that's around 3. 24 quarters, all right, that's around 6, 7, right? So I think I can just get away with the negative 10 to 10. So I don't even need the negatives, but I'll put them in just for, you know, for fun out of habit, right? So then close parentheses, hit enter, and it'll reproduce. And this is how you verify that you didn't just botch it all up. You just take a look. This after you hit enter, it should look just like what you want it to look like, except you have the domain along for the ride. Now I don't see anything here, but that's not alarming. I can just zoom out, and now I have a nice curve to work with. All right, it's like a kind of an oblique parabola. And fun fact, that's exactly what it is. All right, there's a technique that allows you to rotate a parabola and put it in parametric form. It's kind of cool. All right. So what we're going to do here is just verify. Right? So I'm going to put in a t value of 3/2 and see if that plots me, because I'm pretty confident about the math that gave me the coordinates. So I just want to see if the t value of 3/2 leads me to a horizontal tangent. Looking at the picture, I should be in this neighborhood over here, because that looks like where the horizontal tangent ought to be. For the vertical tangent, I should be around right here. And just eyeballing it, that looks like it could be negative 1/2. So I'm going to take my function, which is now defined as a, and using function notation, that's a good thing about GeoGebra and Desmos, is I'm gonna type in a of 3/2 and hit enter, and it put that in coordinate form for me of 3.75 and 2.75. Now, I don't have to do it because I'm very comfortable with my calculations here. That I don't have to do the conversions because I know that 3.75 is equivalent to 15 quarters, and I know that 2.75 is equivalent to 11 quarters. So I'm feeling good about my horizontal tangent. My vertical tangent, I'm going to evaluate a for negative, that the t value is negative 1/2. Pop that in. Negative 1/4 is the negative 0.25. 6.75 is the decimal equivalent of 27 quarters. And that sure as hell looks like it is right at where there would be a vertical line tangent to the curve. Right? So I'm feeling very good about this solution. It took a lot of doing. There's a lot of work involved, but we got there, and now we have a way of verifying our work. Right? And it's all because of GeoGebra. Right? So just a little something to get you going, getting you think about the concept. What I'd like you to do for homework is the next one, page 7, numbers 4 and 5. All right, those involve arc length. It's a lot of plugging and chugging, but we're going to start off class with that next time. So you can see it's just simple. Just do the work.
You want us to do again? Page 7 what?
Page 7, the 2 problems on page 7, numbers 4 and 5. So we'll start off class next time going over these problems, and we'll also talk about unit circle stuff. All right. So at this point, if you want to sign off, you can go for it. And a lot of you should have made some decent headway in the tech assignment, but if not, you can get cracking on that and send me any questions you have. And I'll budget some time on Wednesday to talk about it if people need help with it. All right. So like I said, if you wanna head on out, you're welcome to do so. Have a wonderful evening, and I'll see you on Wednesday. If you have questions, stick around, and yeah, that'll do.